Okay, guys, let's start the second practical session of the school. Is everybody else ready? Yeah? Okay. My name is Kate. I will be a TA for the first part of the seminar, the theoretical part, and the second part, which will be after the coffee break, Nadia will teach. This is Nadia. And we also have two assistants here, Maxim. Please, yeah, stand up. And Oleg, who is not here, I think, but he will be like in 10 minutes. So if you have any questions, don't hesitate to ask them during the seminar of any of us. Okay, today's seminar will be about EM algorithm. And the structure of the seminar will be pretty much the same as for the previous one. So we'll have some problem. We will divide it into several parts, and then you will have some time to solve each part by yourself, and then we discuss the solution, okay? And in the practical part, you will program this final solution in Python, okay? Okay. So the theme is EM algorithm. For the investigation, I will speak a little bit more about investigation a little bit later. First, let's speak. It doesn't work. I'm sorry. Neither. It doesn't work. We have some technical issues. Sorry. Okay. Even though you just listened the whole lecture about EM algorithm, we will like summarize what is EM algorithm, what EM algorithm is in one slide. So EM algorithm is an algorithm for optimization to do inference in probabilistic models with latent variables. So here you have some observed random variables x, some latent random variables z, and some parameters theta. And you have some data. And in your data, you have all the samples of your observed random variable. So the task is to maximize the incomplete log likelihood, this one. But since this task may be quite difficult, we will optimize not this function, but the lower bound on this function. I think everybody like just saw this lower bound in a lot of slides in the previous presentation. Yeah? Yeah. We will optimize it in a block coordinate ascent manner. So we'll have an iterative procedure. On each iteration, we'll have two steps, expectation step and maximization step. On the expectation step, you fix your parameters theta, and you optimize your lower bound with respect to variational distribution Q. And on the maximization step, you fix your variational distribution Q and optimize your lower bound with respect to parameters theta. And since this procedure is iterative, we need some stopping criteria to understand when should we stop. Usually, this criteria looks like this. So we just check then the value of lower bound stop to change. I hope that nobody have any questions right now. Yeah? Okay. Now about the investigation. We'll have one big problem for this practical session and like the other one, so the second one. And the story is the following. As you all know, we will have a game night on Thursday. If you didn't know about this, now you know. And one of our organizers decided to prank us and hid all the games. So the goal for today is to understand who is the prankster and find the games. Okay? What do we have? We actually were able to obtain a set of K photographs of the suspect. But our suspect is a very clever man, so all of them are very noisy. And you can't see the face here. Yeah? Let's do some Bayesian magic and expose the prankster. In more mathematical notation, what we have? We have K images. All of them are of the same size. And all of them contain the same background and the same face of the suspect. The difference between images is the position of the face in the image. So in each image, we have some random horizontal shift decay. And in position decay, we have a face in this image. And also we have all images contain the whole face. So like decay is less than W big minus W small plus 1, I think. And this is noiseless image, and we have some Gaussian noise with 0 mean and variance as square. Okay? Yeah, I didn't say very important parts. Do you see this link? You have like the same things that I have in this presentation, but in PDF at this link. So if you don't understand something that I say, you can go to this link, and the problem statement is there. Okay? Yeah. We also have some printed copies here, but we like trees, so we printed only, I don't know, 20 of them. But if anybody really needs the printed copy, we have them. Okay? Now let's, okay, we discussed the data. Let's discuss the probabilistic model. What is the observed random variable here? Please answer. I hope I will hear you. Images, yeah. So the observed random variable is the set of images, X. And what is the latent random variable? What we don't know. No. No. The position, yeah. The position is a latent random variable, and the phase and noise, not noise, but variance of the noise, and also a background are the parameters. Okay? So what is the probabilistic model? Usually probabilistic model says us how the data were generated. What? We have, as I already said, we have one face, so we have only one suspect, and one background. But the position of the face in the image is random. Probabilistic model. Probabilistic model usually says us how the data was generated. Let's start with the probability of each image xk given the random shift decay and parameters. How this image were generated? What is the probability distribution? Do you have any ideas? Why uniform? Like we already discussed that, like in this case, we already know like the random shift. It's fixed, and all the parameters are fixed. Then what is the distribution for the image? Yeah, it's Gaussian, but actually it's not Gaussian. It's like a probability of Gauss, or product of Gaussians. I'm sorry. The product is because we generate each pixel separately. So we have the product over all the pixels, and we have two cases for the Gaussian. Both of them are Gaussians with variance as square, but the means are different. The first case is for pixels which are inside the face area, and the second one is for the image, the pixels inside the background. Is it clear? Okay. What else do we need to write our probabilistic model? Now we have likelihood. What else do we need? Prior, yeah. The prior is the probability distribution for decay, and we decided to make it like also trainable. We will have a vector of parameters A. The elements of this A are probabilities of the random shift. Like AG says us how probable that decay equal to G. And the elements of vector A sums up to 1. Okay? And the joint probabilistic model looks like this. We simply take a product of likelihood and prior, and then take a product over all the images. This is our probabilistic model, in which we will do inference. Between F, what's the difference between F and what? Between face and background. Let's go back. We have two images. One image of background, this blue one, it's big. And one image of face, the yellow one. And they are, like, face is put over the background in some random position. Okay? Is it the answer? Yeah. Position? Yeah. We discussed this already. Okay, you actually saw pretty similar slide already in the beginning of the presentation. This is simply an overview of EM algorithm, but for our particular case. The only difference is that we have now latent variable d instead of z, and we have two parameters, theta and a here, instead of only theta. All other things are the same here. Now we'll go through the steps of EM algorithm and derive all the formulas. Okay? So we'll discuss E-step, then we will discuss the optimization on maximization step with respect to all the parameters separately, and then we write the stopping criteria. Okay? Actually, the next slide is like, let's do expectation step. So if you have any questions about problem statement, let's discuss them now. Do you have any questions? A is a vector of, let's go here. A is a vector of parameters of size w big minus w small plus 1. AG says us how probable that the fact is that decay equal to j. We train this vector too. So we here we optimize with respect to theta and a. Any more questions? To make you like want to do all the math more, I will say you that at the end of the second part, the most successful detectives will get a trophy. We don't have a lot of trophies, so if you want a trophy, you need to be the fastest one. Okay? Let's do the expectation step. On the expectation step, you simply need to compute the posterior distribution of latent variable d given x and parameters. Now we'll do the same as in the first seminar. So you derive the formulas by yourself. You ask questions, and like in 5 or 10 minutes, we will discuss the solution. Okay? Guys, Nadia asked me to explain you one more time what is this formulation. Does everybody understands that this normal distribution on this random variable with this mean and this variance? Yeah? Yeah, but we have zero mean Gaussian noise on the noiseless image. So the mean is noiseless image. So here we have f and b, so this mean is noiseless image. Okay? What? We add zero mean Gaussian noise to the noiseless image. And this, like, this form of the distribution already use the noise and the noiseless image together. You can say it like this thing is equal to f plus noiseless plus Gaussian noise with zero mean. Let's continue. Okay? Okay, nobody says don't do it, so let's do it. Okay, expectation step. Here you need to compute the posterior distribution of your latent variable d. And first we use the fact that all the images are generated independently. So we have a product here. Then we use actually two rules. First we use a product rule or definition of conditional probability. And then we use the sum rule for the denominator. Okay? And then we simply use the fact that we first generate the latent variable and then we generate the image. Here you have like 2 different probabilities and you know them from the probabilistic model. And in practice, this distribution over D, actually the distribution over dk is a categorical distribution. So you actually need to compute only the denominator and then normalize it to the Q of decay, the sum of Q of decay be equal to 1. D prime is simply the index for summation because we can't have the same index here and here. Is like we sum over all possible values of dk prime. Maybe. I think we can write it like these 2, but I'm not sure. But like, I think you understood what's the fact. Do you have any questions?
Other positions for dk prime are from 1 to width range.
No, the position for decay, for any decay and dk prime is from 0 to w big minus w small plus 1, since all the images contain the whole face. Okay. It's not that complicated. You simply, like, you will program it directly, and that's all. I mean, it's like normal distributions. No? Like about the most, like the best way to compute it in Python, you'll speak with Nadia in the next part. Right now, like, you have it. That's all. Any more questions? Okay, I think you should, like, if you didn't do it by yourself, you should write this formula to have it. We will give it to you too, but like, if you write it in your notebook, it will be better for you. I don't hear, I'm sorry. Product is only one product. Actually, if you have a product, the question was, why we don't have a product in the denominator, like after the sum? Because you can exchange it, like, I'm not sure that I can explain it without writing the formula, but I think we can discuss it, 2 of us. Like, this is the right one. dk prime is simply an index. Maybe I was not right, and I should write like k prime without dk prime. This is in index.
No, dk is prime for dk. It's for yeah, and then write it in a probabilistic manner. Yeah, we can write like sum over j from 0 to w minus w plus 1. And here write probability of xk given dk equals j, and then probability dk equals j. So you may do it. So the main thing here is that you sum over indices from 0 to w minus w plus 1.
So we can't write it k prime. This is a different index. This is not index for the images. This is index for the positions of the face. Okay? May we continue? Okay. We have to continue, yeah. The show must go on. The second part is the maximization step. First, let's rewrite the function which we will optimize in a little bit more simple manner. So you have a function like this is, I'm sorry, this is the part of our lower bound which depends on the theta. So we don't have the second part of the lower bound, the h, I don't remember the name. I'm sorry. This one. We need only this one because this one doesn't depend on the theta. So you need to rewrite this formula using 2 points. First one, here we have an expectation with respect to q of d. And if you think about the random variable d, it's actually a vector of random variables. There are k elements in this vector, so one element for each image. And each element may be equal to 1 of w big minus w small plus 1 possible outcomes. So if we sum up respect to d, it will be a very big sum, like k to the power of w big minus w small plus 1. This is a big number. So let's, since we know that q of d is actually a product of q of dk, let's use it and rewrite this formula in the way that we don't have this expectation and have only the expectation with respect to q of dk. Okay? And the second part is that to make the optimization more convenient, let's rewrite it not using theta, but using the parameter names f, b, and s square. Okay? Should I go to the slide about EM algorithm again or not? Yeah, this one. Let me repeat 2 things. The first one, you do not need this part because it doesn't depend on theta. Okay? It only depends on q, and q is fixed for now. The second one, you already know q. You don't need to use the formula for q for now. You simply suppose you already computed it in some function and you know the values. That's all. Okay? We decided to continue since nobody understands what to do. Yeah, because we don't have a lot of time, so let's be faster. What did I mean when I say that let's simplify the function? First, we will speak about this point. This is our function q, which we want to optimize. This is its initial state. Then we use the fact that we simply use the formula from our probabilistic model. Then we use the fact that the logarithm of product is the sum of logarithms. Okay? Then we can exchange sum and expectation, because expectation is a linear function. So we'll have something like this. And then if you think about one term from this sum, it depends only on one image. So we actually do not need to take expectation with respect to all these. We only need to take expectation with respect to q of dk. Okay? Is it clear? I think yes. The second part. This is the result from the first part. The second part. We simply write formulas for logarithm of log likelihood and for the prior. This is log likelihood and this is prior. I have very strange, like not strange, but new notation here. I have two masks, IF and IB. This is simply binary masks, which says us whether the pixel is from the background or from the face. Okay? So this is part, let's speak a little bit more about this long formula. This part is from the normalization constant of normal distribution. This part is from the exponent of normal distribution for the pixels from background. And this is part from the exponent of normal distribution for pixels from the face. Is it clear? Like, I think this part is clear. Like, it's our prayer. That's all. Okay? You will have this formula on the next slide. Don't worry. Okay? Continue? Continue. Okay, now we have our formula. Let's maximize this Q function with respect to all the parameters. As Nadia suggested, let's do the optimization with respect to A together, and then you will do the optimization with respect to all the other parameters by yourself, okay? So this is our long formula of Q. This is the same formula as on the previous slide. I simply like combined all together. And for vector A, since A is a vector of probabilities, we have some additional condition for A. Okay? If you look more closely on this, at this long formula, you'll see that only this part depends on the A. Okay? All other parts are constant with respect to A. So we actually don't need this long formula, we need only this one. Okay? What do we need to use to optimize the function with some additional condition? You should already know this from the first seminar. Lagrangian, yeah. Lagrangian looks like this. It's very simple. Then we take a derivative of Lagrangian with respect to A and with respect to our Lagrange multiplier lambda and make them equal to 0. Is it clear? I think it's like it's very like very simple formula here, so it should be simple. So the answer is this one. So AJ is equal to this fraction, where the denominator equals to this value of lambda. In practice, it's the same thing as with our Q distribution. It's a simply, A is a categorical distribution, so we only need to compute the denominators and then we normalize. Okay, do you have any questions right now? Now we want to optimize our function Q with respect to F, B, and S square. It will be easier because we will not have any additional conditions. So you will simply need to compute a derivative and make it equal to 0. Okay? The first one is the optimization with respect to F. Let's continue. I will give you the answer, so. Okay. Here in this long formula, we actually also don't need all the terms. We only need this one. It's clear, yeah? Because we care only about the face. So the optimization problem looks like this. This is simply a sum of quadratic formula. We take a derivative. Oh, no, we actually don't take a derivative just for 1 second. We want to find pixels of face. So we want to find the derivative with respect to F, I don't know, IJ. And we have decay here in the indexes. And decay is different for all the terms in the sum. So we want to drop it somewhere, and we drop it here. So we simply say that, okay, now we have new index m. It's equal to j minus dk. Okay? So we indexing not the image, but the face. Now we have simply FIM, and we can take a derivative respect to FIM. It's equal to this. And from this formula, we see that FIM is equal to this fraction. And we actually, if we sum up this denominator, we see that the sum of q of dk respect to dk is equal to 1. And we have a sum over k of 1s. So we have k, the number of images. Okay? Let's look at this like for 5 more seconds. Understand that everybody understands what's going on. Yeah. There is the indication function. Okay. Then we drop this decay from here. We actually have a sum here only over the image of the pixels in the face. Okay. So m is from 0 to w small minus 1. So here we don't need indicator anymore. Any more questions? Okay, we should continue, yeah? The next part is like, looks the same. We need to compute the derivative respect to b and find b. What? Yeah, it's pretty much the same. It's actually even more simple because we don't need this trick with indexes. Should we continue like this, or you want to write it by yourself? I don't hear you. Let's continue. We want to eat. Yeah, okay, you want to eat, I understand. Okay, here we have the same thing. So we use only this part of the formula. We have a much more simple optimization problem. And here we just compute the derivative respect to some pixel from B and make it equal to 0. And this is the answer. Here we need our mask because we need to use all the pixels from the image. We can't use different indexing because background is big and face is small. Okay? Okay. The last part, S square. You have a question? Yeah, yes, let's.
What happens if there are some pixels that do not belong to background
Then you will have some gray result for these pixels, and that's okay. But you will actually have a lot of images, so I think will be no problem with background pixels. Okay? Yeah. There is no stupid questions, actually. What do you mean? This function is not discrete. This b is discrete. And I take a derivative respect to 1 pixel of b.
Yeah, but the input variable is discrete, right?
B is not discrete. It's like a value of pixel, and since we think that our image is generated from a normal distribution, it's not discrete.
You said it is a bitmap, right? So it's either 1 or 0.
No. The bitmap is this, IB. Is either 1 or 0, so it's 1 if this pixel is from the background. And Bij is the value of this pixel. So if you have a noiseless image of background, Bij is the pixel of this noiseless image. Okay? Any more questions? Almost the last part. Let's optimize with respect to S squared. Should we continue? We actually have only, I think like 10 minutes, so yeah, we'll continue. Here we have a little bit more terms which depends on the S square. We actually have 3 of them. So the derivative will be a little bit more complex. We take it, this is a, like, we drop this first one, the first term. This is our optimization problem. We take a derivative with respect to S square. It's very long, but it's not complicated, I hope. So you take a derivative with respect to S square, and you have this long sum. So this is a derivative of the logarithm. This is a derivative of the part about background, and this is a derivative of the part with phase. And if you like rearrange these terms somehow, you will have a formula for S square, which looks like this. And actually, this sum in the denominator is also, then you sum over dk, it's equal to 1. And then you sum over number of images, number of pixels in the row, and number of pixels in the column. So you have n, or we have n. It's not n, it's k. I'm sorry. We have k here, a number of images. And w is the width of the image, and h is the height of the image. Okay? This is like actually like formula for the variance. Like usual formula for variance, I think. Okay? Do you have any questions? You want to eat, yeah? And you don't want to think about formulas. Yeah. Yeah, but like, we don't care about the unshifted estimation, so. Any more questions? Okay, the last step. When we should stop? Actually, there is a very simple answer. We can stop after, I don't know, 1,000 iterations. And that's all. We may not compute this thing at all. But we can. So to compute the stopping criteria, you need to compute the value of lower bound. And we continue. Yeah, we continue. To compute this value of lower bound, we actually use pretty much the same tricks as we used in the slide. Then we rewrite the formula of the function for the optimization. Remember, we first rewrite the function which we optimized in M-step, and then we optimized. This is all the same tricks. This is the formula for our lower bound. We use our probabilistic model. So we rewrite it as a product. Then we use the rule that the logarithm of product is a sum of logarithms. When we exchange expectation with sum, and then we say that, okay, we have expectation with respect to q of decay, since this term for 1k depends only from one image. So these are like all the same tricks. But earlier in the M step, we had only this part, so the logarithm of log likelihood. And now we have the second term too. Okay? Do you have any questions? What? The stopping criteria. Stopping criteria is this, the first line. So then you program your EM algorithm. You compute the value of L on each iteration. And you remember the value of L from the previous iteration. And you simply like compute this difference between them. And if it's smaller than some small number, then it's OK. You should stop. Make 1,000 iterations? then the question was why shouldn't we just check the difference on the expectation step and on the maximization step? And I think you mean that why we don't use the difference in parameters. Yeah? Like the previous value of theta and the new value of theta, and let's compute the difference. Yeah? Usually we should use L since it's like one number, and parameters may be like the vector of 1 million elements. That's easier. It depends on what? Yeah, so, okay, you can compute the difference between the vectors of parameters and then compute the norm of this vector. That will work too. I'm sorry, I can't hear you. Why? Okay, yeah, maybe if we, maybe from after some steps, something may drop something. I'm not sure. Like this is like the whole formula, and it depends on the fact then when we. Do you have any questions? This is the result of everything. Do you have any questions? Do you understand all the names of variables and such stuff? You will have these formulas in your IPython notebook, so don't worry, don't make a photo. Yeah. So is it okay? Do you have any questions? I think it's okay.
Hello? Hello? Does it work? Yeah. I think we may discuss remaining questions in the coffee break, during the coffee break. The important thing that for the second part of the seminar, we will need data. We have given the link to it yesterday, but if you didn't download it, please do it. Okay, who has already downloaded data? Who didn't? See, internet now works. However, we cannot guarantee it will work in a half of hour, so please download it during the coffee break. And also, I just posted the link to the notebook with prototypes of the code. Please download it during the coffee break too. And I will put these links to the whiteboard now too. So have a coffee break and don't return to our seminar.
If you don't have internet still, please find me. I have internet at my phone. I will help you. Maybe not all of you, but some of you. Okay? Yeah. The slide will be, slides are not online yet. We will, I think I will post it just now. But you will have all these formulas in your Python notebook, so don't worry.